Okay, good. So we can start again. So to give a brief recap of what we did this morning, we had, I'd say, an introduction to the cryptographic properties of Boolean functions and S boxes that are, let's say, the most commonly used primitives in the design of stream and block ciphers. So we are talking about the symmetric key cryptography setting. And then we noticed that these functions need to satisfy some kind of properties for security in order to withstand specific cryptanalytic attacks. And so we can also cast these properties in terms of an optimization problem, in terms of a combinatorial optimization problem. So we have constraints like trade-off between nonlinearity, resiliency, and so forth. And we have also the problem that the number of the whole number of Boolean functions in n variable is growing like super exponentially in the number of input variables n. So we have 2 to the power of 2 to the power of n possible functions. So we cannot do exhaustive search. This is the reason why we use combinatorial optimization algorithms, especially coming from the AI domain. So the optimization algorithm called also meta-heuristics, like evolutionary algorithms and swarm intelligence algorithms and the like. So we described a bit how evolutionary algorithms work. And now we will see how to apply this to design Boolean functions and S boxes. So we start with the first kind, let's say, of search, the, let's say, easiest way to represent a candidate solution in our space, if we are talking about a Boolean function of n variable, is to encode it through its truth table vector, right? So basically we have our function that will have the, now I'm still doing with n equal to 3, but in general we assume that n is strictly greater than 5 because otherwise we can do exhaustive search. And in practice, we aim for Boolean functions of 8 variables, especially if we are considering the S boxes settings where each coordinate function is a function of 8 variables. If you're just using the combiner model for the pseudorandom generators, usually we have something that is between, let's say, at least 13 variables and something around 20 variables. This is because if you, in the combiner model, if you use something that is smaller than 13, then you can use some other kind of algebraic attacks. And basically, even if you have an optimal Boolean function, then it's basically useless. So you always want something that is higher than 13 in practice. But actually, we will see that these algorithms have been studied, especially like in the case of 8 variables, mostly for benchmarking reasons and to see if they were like interesting to see in the first place. So this is just a matter of practicality, let's say. Practicality. So we have our truth table. So from 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, and so on until 1, 1, 1. And then we will have 0, I don't know, 1, 0, etc., 1. And this is a 2 to the n bit vector. So we need to find the correct sequence of zeros and ones in this vector such that the corresponding Boolean function has optimal cryptographic properties of balancedness, in particular, algebraic degree, nonlinearity, and resiliency. We saw this morning. So we said that genetic algorithms, in particular, they use bit string representation for the candidate solutions. So this is very straightforward and natural. We just say that this vector here that represents our Boolean function will be the genome, let's say, of the genetic algorithm for a candidate solution. So all our functions inside the population of the genetic algorithm are represented as bit strings of length 2 to the power of n. And the fitness function, on the other hand, is the function that we want to optimize with the genetic algorithm. And it measures how good is a Boolean function with respect to the properties that we want to optimize. So usually there are various fitness functions in the literature for this problem, but mostly they target nonlinearity, algebraic degree, and deviation from correlation immunity or resiliency. So the idea is that we want to have our fitness function. So it will be something like this for a Boolean function f of n variables. To be something that, for example, maximizes, so measures the nonlinearity of the function, because we said that we want the nonlinearity to be as high as possible to thwart the linear cryptanalysis attacks or fast correlation attacks. We also want to maximize the algebraic degree. So we'll have something like this. And then we want to minimize the fact that they are unbalanced, so that they don't have the same number of zeros and ones in the truth tables. So alpha of zeros and alpha of ones. So we will have something like minus the unbalancedness of f. So this basically measures how many bits needs to be corrected in order to get a Boolean function. And finally, also the deviation from correlation immunity. So if we fix correlation immunity, which, like I said, is basically a resiliency without balancedness. So we can still think of resiliency in general. So basically, it means that the Walsh transform of the Boolean function f computed on a vector A needs to be 0. And this is for all vectors A in f2 to the n, such that the Hamming weight, so the number of ones inside A, is included between 1 and t. So if we have this condition here satisfied, then we can say that the function is T correlation immune or T resilient. So how do we obtain, or how do we model this as an optimization in a fitness function for a genetic algorithm? Well, basically, we do something like saying, okay, for each of these coefficients that I'm targeting with a Hamming weight that is between 1 and t, then I'm computing the coefficient and I'm checking if it is 0, then I'm not adding anything to this penalty. Otherwise, I will add, for example, in absolute value, the coefficient of this particular vector here. So we will have something that we call, let's say, res dev, so the deviation of resiliency, which I'm not writing it in full, but basically is summing all the deviations of the single vectors here that have Hamming weight at most t. And this will be the deviation from resiliency of the function f. So we are maximizing this nonlinearity and algebraic degree, minimizing the deviation from being balanced and the deviation from being resilient, which are the 4 properties that we targeted for Boolean functions this morning. So basically, we want, in the end, to maximize the fitness function T for a particular argument. So this is for, we saw how to encode our solutions with genetic algorithms. So how to define a fitness function, then you will see that in various papers in the references that I put in the final slides, there are different variations. Sometimes you only consider nonlinearity, for example, sometimes only resiliency and so on, or a combination of this subset of these properties. Now we need to see how to do the genetic operators, so the crossover and the mutation. So for crossover, of course, we could use the simple one-point crossover that we saw this morning. So we select between 2 different parents, let's say a random cutting point, and then we exchange the portions of the genomes of these 2 parents to get 2 new children. The problem is what? The problem is that if we want to retain, or let's say, we could do it and then minimize the unbalancedness deviation at the level of the fitness function. So we could do this, okay, I take unbalancedness as something that is criterion to optimize. So I just like the genetic algorithm to search among all possible 2 to the power of 2 to the power of n Boolean functions. And I'm also considering this particular criterion for optimization. But we can do something a little bit smarter, let's say, because we could say, okay, we can craft some crossover and mutation operators that will preserve the balancedness already. So starting from an initial population at the beginning of the genetic algorithm that are where all functions are balanced is quite easy, because you just say randomly, you say, okay, I have basically to permute a set of 2 to the power of n minus 1 once over a string of length 2 to the power of n. So, or you can do it like in several ways, like you could do it, let's say, let's put it here. You could say for initialization, oops, classic init. So you could say that you have like your string of length 2 to the power of n, and then you choose randomly how to initialize each bit in a certain order. You decide it randomly. If you put a 1, then you're going to increase a counter. So for example, if you're going to put a 1 here, then you will have a counter for 1s that is increased by 1s. And every time you're going to check whether CNT1, so the counter, has reached 2 to the power of n minus 1. So if we reached half of the number of the length of the table that is filled with 1s, then we fill all the rest with zeros. So doing that with the initialization is very simple. We don't need anything fancy for that. For crossover, we need to be a little bit more careful because, of course, we are dealing with 2 different parents. So as you see here in these slides, we have 2 parents that are balanced. We want to make sure with crossover that they are the children that are coming out from this are also balanced. So the idea here is to use counters, and this was an idea that was introduced initially by Milan and others in 98. So basically, we still have a counter for 1s and a counter for 0, and we go from left to right in the construction of the child. So we start, like you see here from the slide, we start from the first bit, and then at the first bit, we will say, okay, we choose with a random, let's say, uniform distribution, so 50%, 50%. I copy either from the bit from the first parent or the bit from the second parent. And at that point, I'm going to update the relevant counter. So if I copy the 0, then I'm going to update the counter of 0. Otherwise, I'm going to increase the counter of 1s. At each point, we are going to check whether one of these 2 counters reached half of the length of the truth table, so 2 to the power of n minus 1. If that's the case, so as you see here, when you arrive at the position, at the 6th position, we reached a number of 1s in the counter of 1s, that is 4, which is the half of 8. So we fill all remaining positions with the complementary value in order to retain the balancedness. And in this way, we are sure that we always get something that is balanced. For mutation, well, it's a little bit simpler because we said that for mutation, usually in genetic algorithms, we employ bit flip mutation. So for each possible position, we say with a certain low probability, we flip the value of that bit. In this case, it's always the same thing. So we are still doing that with a low probability, except that we are not flipping the value, so from 0 to 1 or from 1 to 0, but we are swapping it with another randomly chosen bit inside the truth table. So in this way, we are always swapping and permuting the same bits, and this means that the Hamming weight is preserved, and so it's also the balancedness. So this is for crossover and mutation. Next, we also saw genetic programming. So in genetic programming, like we said, instead of having a representation with a bit string, as in the genetic algorithm, we have a syntax tree. And the syntax tree, like the meaning is that we have the input variables of our Boolean function as the leaves of this tree. So here we are taking 3 input variables, so x1, x2, x3 only occurs at the leaves level. And then we are combining them with the internal nodes of this tree that represent Boolean operators. So for example, here we have x1 and x2 that are combined with this plus that is an XOR. So we are computing the XOR of x1 and x2. And x3 is converted into the complemented version by using a NOT operation. And finally, the output of these 2 nodes is combined once again at the root of this tree. There we use a logical AND, so we do the AND of these results of these 2 operations. And what comes out from this syntax tree, so at the root from there, will be the output of our Boolean function. So this means that if we evaluate the tree for all possible combinations of the leaves node, so 2 to the power of 3 in this case, 8 possible combinations, then we can synthesize again the truth table of the function once we have fixed an order for the variables. So this is okay, and we said that for genetic programming we have crossover operators and mutation operators like subtree crossover and subtree mutations, which means that, for example, if we have 2 trees, then we are selecting a random subtree, a random point of those 2 trees, and then we reselect, let's say we swap actually those 2 subtrees. And for mutation, on the other hand, we just say for a single parent, we say, okay, from this point randomly chosen, we are reconstructing a random subtree from there. What is the problem with this? The problem is that it is very difficult to enforce constraints on the balancedness of the solution. So like we said, here was very simple because we had this simple structure. We can use counters, and in this way we are able to keep track of the multiplicities of the ones and the zeros and get in the end something that is always balanced. Here with a representation with the trees, it's actually very difficult. To be honest, I don't know how to do that. I tried to think over it for many years. I still haven't come up with a decent solution. I think it's kind of difficult, really, from a theoretical point of view, to say, okay, you want to select like let's say a crossover operator that is always able to produce syntax trees such that the corresponding output, so in the truth table, is always balanced. So it is possible, let's say, to say, okay, if we start from something like a tree that has already a structured shape in a certain sense, then it is possible. The problem is that by constraining the search space in this way, you're not, let's say, representing the whole search space that you're interested in. And this could be a problem because maybe you're getting stuck in local optima or you're not finding the best possible solution. Nonetheless, apparently genetic programming has usually better performances than GA. So we have this curious thing that if you take the space of all possible Boolean functions, so we said that, let's call it like Bn, this would be the set of all Boolean functions of n variables. The cardinality of this would be 2 to the power of 2 to the power of n. So the genetic algorithm is, let's say in the generic case, where it doesn't use any balanced crossover, is always looking at this whole search space. Instead, if we are using balanced crossovers or balanced mutations, then it is searching for something like, let's call it B star n. We need to calculate this in the following way. So we have something that has length 2 to the power of n, which is the length of a single truth table. And inside this, we need to choose 2 to the power of n minus 1 positions set to 1. So positions set to 1. So the number of choices that we have will be the binomial coefficient of 2 to the power of n out of 2 to the power of n minus 1. So this is something that, if you look at it from an asymptotic point of view, it doesn't change that much from here, let's say, from the original search space. But actually, in practice, this gives, like, especially for smaller values of n, this gives like a huge advantage in the sense that the search space is quite reduced by a great deal. Let's say it like that. Unfortunately, this fact that the search space is reduced doesn't help the genetic algorithm with balanced crossovers and mutations. And on the other hand, genetic programming is not only watching at this search space with unconstrained operators, but it is searching something that is even bigger, because in the fact is that we can have different syntax trees that are mapping to the same truth table. And this is quite easy to see, because if you see it from the slide here, you could have like a lot of what is called bloating in genetic programming. So you could have like a very huge expression, a very huge syntax tree, where you have a lot of factors of nodes that are canceling out each other. Like, for example, you're computing here twice the knot, for example, or you're computing like an XOR with the same variable, which is a 0, or you're computing the XOR with something that is a variable plus a 0, so it's always the same. So you could have a lot more of trees, and actually you need to constrain the depth, at least, of the tree in order to say, okay, you have this number of trees that you can search in total with genetic programming. Yes?
This still seems like a little bit of a trap, because then you have a big expression, long, genome, but it doesn't express anything, and you are still spending a lot of time on mutating, crossover.
Yeah.
So is it even feasible to do some sort of factorization, or?
You can do this, like one of the standard techniques in genetic programming is to do some interpretation of the solutions produced by genetic programming, and this usually entails to simplify the expression. So finally, you like prune a lot of unnecessary nodes, and that is usually the best way to approach this. We will actually see this at the end of the lecture when we will talk about evolving constructions, where we did also some, like this in my work, some of this simplification using Boolean minimizers, basically. But yeah, you're right. I mean, in general, genetic programming is dangerous in the sense that it could like create something that is very useless in practice because it is so huge, but luckily we can usually simplify it. And the sheer fact is that if you look at it from an empirical point of view, genetic programming is still outperforming genetic algorithms by far. Like, it's very efficient to do this. Okay, there is a broken reference there, but I will fix it later after I will put the recording online. And it's the reason why this is happening is still unclear. We think that genetic programming has some smarter way, in a certain sense, to learn the distribution of Boolean functions by using this particular representation, something that you cannot represent like with a similar structure with binary strings. Okay, now we go for something a little bit different. So this was the part about using evolutionary algorithms, using to optimize Boolean functions, so single output Boolean functions. Now we consider the case of S boxes, so vectorial Boolean functions, let's call it big F, that maps from F2 to the N to F2 to the N. So this is the case of the S boxes that we saw, for example, in case of the AES algorithm yesterday, or the substitution permutation networks in general. And Here, actually, one could use evolutionary algorithms also to genetic algorithms or genetic programming to search also for optimal S boxes, where in this case we are targeting nonlinearity. So the fitness function would be something like, let's cancel here. So here we would have a function big F, and it would still maximize, let's say, the nonlinearity of the function, which I remind you is the minimum nonlinearity among all possible component functions, so the linear combinations of the coordinate of the S box F. And then we want to minimize, well, we have also bijectivity, of course, so we have still to minimize the unbalancedness of F in order to get bijectivity. And then we also want to minimize the differential uniformity, so delta of F. We want this to be the smallest possible, and the smallest possible was 2 in order to get an APN, or an almost perfect nonlinear function. And then we always want to maximize this whole formula, let's say. So we could still do it with classic genetic algorithms with the same representation. We won't have just a single bit string. We will have, let's say, a matrix of bits that specify specifies the values of the output vectors of the S box. Actually, what I noticed, like in my research experience during my PhD, is that you can use a simpler model in order to get very good S boxes. And this simpler model is based on cellular automata, which I was telling you, it's, let's say, you can consider it as a kind of artificial intelligence model, because in the beginning it was used to model especially self-reproduction behavior in dynamical systems. It is still done today, although in a different fashion than what it used to be by John von Neumann back in the 50s, I think. Here instead we consider cellular automata not as a dynamical system, as it is usually done in the literature on cellular automata, but we are considering it as an algebraic system in a certain sense. So it is a very specific kind of vectorial Boolean function in a certain sense. So we have, let's say, a finite array of n cells. Okay, this will be the input of this cellular automaton. And then we have what is called, so each of the cells inside this array can be in a state either 0 or 1. And then we have, let's say, what is called a local rule for this cellular automaton that is defined by a diameter. So the diameter is telling you how many cells each cell is looking in order to compute its next state. In our case, the local rule would just be what? Would be basically a Boolean functions of d variables. So d is the diameter, will be the number of variables for our Boolean function. And then we compute the output for each cell by applying the local rule to the neighborhood relevant to that cell. So for example, we have here on the left these 6 cells cellular automaton, and the diameter is 3. The local rule is the XOR simply of the 3 cells in the neighborhood. This is also called rule 150, because if you look at the truth table of this Boolean function and then you convert it in decimal format, you get 150. And this is also called the Wolfram convention or Wolfram coding, because it was introduced by Stephen Wolfram in the 80s. But anyway, basically this Boolean function just XORs the values of the 3 cells in the neighborhood of diameter 3. So each cell, we start from the left, we'll look at itself. So this one here on the left will look at itself, and the 2 right neighbor cells, so 0, 0, and we will compute the Boolean function rule 150 on the neighborhood 1, 0, 0, basically. So the output will be 1, so we will put 1 in the first output cell of our cellular automaton. And then we continue like this by shifting one place to the right, the neighborhood. So for the second cell, we will compute it for 0, 0, 0, and the output will be 0. And then we do it again, will be again 0, 0, 0, so 0. And we put a 0 in the third cell of the output. And finally, we have 0, 0, 1, and we apply and have XOR of 0, 0, and 1, which would be 1. Here you can see that on the left, we are considering what is called a no-boundary cellular automaton. So we say, okay, we continue to look at our cells and the two cells on our right, but what happens when we hit the end? Like we cannot compute, for example, the local rule of the fifth and the sixth cell in this case, because we don't have enough right neighbors. So in the no-boundary case, we just say, okay, we stop there, and we will have an output which will be smaller than the initial input. This tells you also why we are considering them as algebraic systems and not dynamical systems, because if you're in this setting, you cannot iterate it for many. You can iterate it, but you will have something that is smaller and smaller as time passes. So at a certain point, you will have no cells anymore to update, to apply your local rule. So this is the no-boundary case. Otherwise, we have the periodic boundary case, which is quite common in the cellular automata literature, where basically we say, okay, the finite array of n cells, I look at it as a ring, basically. So the last cell will be followed by the first one, basically. And in this way, we can apply the local rule to all possible cells, and we have a state size that is stable. So we have the same number of input and output cells. Okay, questions so far? Yeah?
So it's not going to be a computational model?
Yeah, I called it here like a parallel computation model because in, let's say, usually in the cellular automata literature, it is used to compute things like using it as a, let's call it like a dynamical system. Yeah. Okay. And here it's, yeah, in the game of life, you have something like a dynamical system. That is true that is a two-dimensional cellular automaton, but the concept is correct. So there you can iterate to infinity, the game of life. And also, for example, a periodic boundary cellular automaton, you can iterate it to infinity. The problem is that since you have a state space that is finite, again, after 2 to the power of n iterations at most, you will go back to, you will fall into a periodic orbit, basically. Here instead, we are just, let's say, interested in the one-shot application of this, of the global rule of the cellular automaton. So we just do one step of the CA, because this is enough for our goals to define a substitution box, because in the substitution box, then you say that after that you iterate it, but in another way. If you remember the diagram for the block cipher in the substitution permutation network, we are doing like several rounds where we are alternating one application of the S boxes with one application of the permutation layer. And then we continue to do it like for several layers. But at that point, you are like considering it, the block cipher, as a kind of dynamical system, which is still finite also in the iteration, but you don't rely like on the fact that you are using no boundary cellular automata, for example, or periodic boundary for that matter. Okay, so what is the motivation for using cellular automata for cryptography? Yeah, that's yeah, because that was actually a very fashionable idea back in the 80s. Especially Stephen Wolfram was very fond of, well, he's always fond of cellular automata also today. If you look at Mathematica or those kind of software, Wolfram Alpha and whatever. But actually in the 80s, he came up with this idea since he was studying, like he was classifying the set of local rules of diameter 3, so what are called elementary cellular automata. And he was classifying them with respect to their dynamic behavior. So he was saying, okay, if I have something that is converging immediately to an equilibrium point, a fixed point, then this would be class 1. They are the simplest cellular automata that you can think of. Then there are class 2 that are periodic, of periodic nature. So for almost all initial condition, you always end up like in a periodic orbit with a pattern that is repeating. Otherwise, you have the class 3, which are, let's say, those that were interesting for cryptography back then, that are the chaotic cellular automata. So you see like a lot of, let's say, complicated patterns inside the space-time diagram of a cellular automaton. And in particular, one of the most famous local rule in that sense was Rule 30. And then you have the fourth class, which is called the complex class of local rules, where you have not just chaotic patterns, but you have something more structured, in a sense that you have a mixture of regularity and chaos that is basically constructing complicated or complex patterns. An example of this rule is rule in the one-dimensional case is rule 110. That was actually proven to be also computationally universal. So you can, using this rule here, you can also simulate any Turing machine. And this tells you that cellular automaton as a computational models are universal. But anyway, for cryptography, basically we consider cellular automata from the class 3, like Rule 30, because since they are chaotic, I don't know how many chaos theory you know, but basically the idea is that if you have a dynamical system that is chaotic, it means mostly that it is sensitive to initial conditions. There are a lot of other small technicalities, but we won't delve into it. The idea is that if you have this, let's say, system that is defined inside this phase space, and you start with two initial conditions that no matter how, well, they're not the same initial conditions, but they are maybe very, very close. And maybe we are not even able to distinguish them because of measuring problems, because we have like finite precision. So at a certain point, we cannot differentiate with infinite precision. So they have a small error in this initial condition. And if you iterate these two initial condition by applying this, let's say, chaotic systems that is defined by a map F, at a certain point, you will see that they will start to diverge. And as time passes, they will continue to, well, not necessarily, but usually you can consider this that they are like diverging more and more. So if you start from very close initial conditions, you end up with a dynamical evolution that is completely different after a while. This is called sensitivity, SCI, or sensitivity to initial condition.
That's why it's so important in applications to define the right initial conditions.
Yeah.
As much as you can, because
for modeling, yes, is quite important.
Especially if you're doing something iterative, like cellular automata,
yeah,
or any other iterative.
Yeah, precisely. In any iterative dynamical system, yeah. So the fact is that these kind of properties like sensitivity to initial condition is actually interesting for doing cryptography in a certain sense, because you say, okay, I want to exploit this chaos that is coming out from this kind of mathematical structure to do something that is unpredictable. So in the end, a pseudo-random generators, like in the Vernam-like stream cipher, is something that cannot be predicted too easily by an adversary. So we say, okay, why don't we use something that is chaotic, like chaotic cellular automata, to do unpredictable pseudo-random number generators? And then the second motivation is the motivation of efficient implementation. So cellular automata are very efficient in the sense that they are a massively parallel model. So they can be implemented, especially in hardware, in a very efficient way. So these are the two main motivations. And now, yes, this is, let's say, some history of cryptography based on cellular automata, which is the idea that initially was proposed by Wolfram. So the idea is that we use this chaotic rule, Rule 30, And then we start with a cellular automaton that has, for example, periodic boundary conditions. Here we are considering it as a dynamical system, so we iterate it for several time steps. So the initial condition of this cellular automaton will be the seed of our pseudo-random generator, so the secret key. And then we iterate this cellular automaton for several time steps. And we sample, let's say, the trace of one, for example, the central cell in this cellular automaton. And this sequence of states assumed by the central cell will be the key stream that we use then in the Vernam-like stream cipher. So the problem, this looked very cool in the beginning in the 80s. And the fact was that Wolfram, since he was not, let's say, his field is simply is not crypto, so he was claiming like security properties of this out only of statistical and empirical tests. Like he was using, I don't know if you have any knowledge of dynamical system theory, but you can compute like Lyapunov exponents or these kind of things to see the stability of the system and say if it is sensitive to initial conditions or not. So he was applying this kind of test and he was saying, yeah, okay, this basically is secure because it is sensitive to initial condition, it is chaotic, and so on and so forth. Actually, it was later shown like a few years later by Meyer and Staffelbach in 1991, I think, that this cellular automaton was quite vulnerable. So it is possible by just looking at this, let's say, trace, so the central cell, it is possible to reconstruct the initial sequence by doing some guesses. So the idea is that you have the idea of the attack. I'll show you. We won't delve into the details, but just to let you know why cellular automata used in this way are not used anymore in cryptography. So the idea is that you have like your initial configuration of your cellular automaton, and then you will have, let's say, the central cell that is your key stream. So this can be observed by an external attacker. So actually, the structure of Rule 30 is something like, if I remember correctly, x1, x2, x3 should be, if I remember correctly, it's x1 logical or x2 XOR x3. So it is something like this. Maybe it's the other way around, like it's x1 that is XORed with the OR of x2 and x3, but anyway, it's the same thing. So the idea is that this tells you that this rule here is not completely nonlinear, but it is quasi-linear, because you have this variable here that is appearing only summed, let's say, with an XOR. So it is not appearing here in the OR. So you can exploit this to basically do a partial reconstruction. So if you know all this, you can say, okay, I don't need to guess the whole initial state of the cellular automaton, which is 2 to the power of n as a search space size, but I need to guess only half of it. So this half here, okay? And then once you do, so you guess this and you check that it is consistent with this trace here, basically. So you evolve it forward to see that it is like satisfying this particular trace. Then at this point, you can exploit this quasi-linearity to reconstruct the second half. So you go backward, and to do that, like there is an algorithm to compute the preimages having at your disposal like this triangle here. And in this way, you can determine this half. So this means that first, you're halving already your search space. So the attacker does not need to search for all possible seeds, let's say initial condition of size n, but actually only those of size n divided by 2. And beside this, there were also other problems with this rule, and in particular, the fact that it was not one resilient or immune to correlations of the first order. And this is the properties that we noticed before that we discussed this morning. So basically, this would give rise to some correlation attacks that would shrink even further the search space that the attacker had to see. So basically, a research thread in this field was to basically choose other rules that were larger than root 30. So instead of using diameter 3, where you have 256 possible roots, then you would get, for example, d equal to 5. And in that case, if you look into Boolean functions of 5 variables that can still be searched exhaustively, you can find rules that are chaotic in the sense of Wolfram and also satisfy a better combination of correlation immunity, resiliency, and nonlinearity. But still, the problem is that this particular way of using cellular automata for crypto basically is died out because they said, okay, there is still the problem that you can always reconstruct, you only need to reconstruct half of the seed, because in order to get chaotic rules, one simple way with cellular automata is exactly to have this kind of structure, so this quasi-linearity, because this is telling you that any difference that you have in the initial condition, for example here, will propagate in this direction. For example, if you are summing, if you are XORing the rightmost variables, and if you are doing it also like x1 XOR x2 x3, then the differences are propagating in both directions. So there is still this problem in the end. And that is why now we turn into something that is used in the real world. So actually, cellular automata turn out to be used also in practical crypto systems, only that they are not called like that. Because people who were studying them, well, in the beginning, they were calling them cellular automata. Then, I don't know, probably for some reason of saying, okay, I'm not associating to that line of works that were shown already to be broken in a certain sense. We are calling it in another way. They were calling it shift invariant functions, but they're basically the same. Shift invariant functions it's the same thing.
Even in master's class, people will give it as names.
Yeah, exactly. Because when you're considering cellular automata in the infinite case, you have the characterization given by Curtis Hedlund-Lindon theorem that says that a function over the full space where you have like the infinite strings, let's say, is a cellular automaton if and only if you have shift invariance and if it is uniformly continuous with respect to the counter distance. If you're considering finite cellular automata, uniform continuity is trivial because it is all finite. And so you just need to say that to characterize a cellular automaton, you need shift invariance. So yeah, they're precisely the same thing. But they call it like either shift invariant or rotation symmetric also functions. But they're still cellular automata.
They're in denial.
Yeah. No, actually, they're not exactly in denial in the sense that, for example, one of them is Johan Damon that I've known in Radboud, who was one of the inventors of AES that we saw yesterday, and also this Ketchuk algorithm for hash functions that has been standardized in the SHA-3 standard for cryptographic hash function. And if you look into his PhD thesis, which is quite nice actually, I recommend it to you. You see that he is basically deriving again some of the results that were known in the cellular automata community, but basically studying them only in a setting of block and stream ciphers, let's say. So it doesn't call it cellular automata, these kind of transformations, but basically they are the same, and he also recognized it. So it's not a huge deal. Anyway, in this hash function, Ketchuk, we have this cellular automaton that is quite simple. So it is the local rule is that one that you can see there on the top, which in Wolfram convention corresponds to rule 210. And this has a nice property in the sense that this cellular automaton is equipped with this rule is invertible if and only if the size of the cellular array is odd. So if it is odd, then you can invert the dynamical evolution, let's say, by using not a cellular automaton, but using a sequential algorithm. So you have something like this, which is the initial configuration, and then you have in periodic boundary conditions, you have f of x. So you know this and you want to determine this. So the idea is that you start with something that is called a seed, so you know at least one bit of the preimage. For example, here, you know that it is like a 0 or a 1, and you can try, basically, you can do different guesses. And then you say, okay, if the length is odd, then I can determine by the structure of that rule what is the value of this cell here. So this is still undetermined, but I can determine that this is, for example, a 1. And then I continue like this, so I jump 2 by 2, and I continue until I arrive basically here, like going the other way around. So I arrive here to determine. So you have determined all the odd positions, for example. And then I do the same thing for the even position. And then you can do it like this, like jumping in 2 and 2, and then you can reconstruct the whole preimage. If you do it like with an even-sized cellular array, this trick won't work anymore because you will basically run out. You will see that you cannot complete everything, basically, using that particular rule. And in this case, in Ketchak, it is used with a state size that is quite small. So it is 5 bits, and 5 bits in input and 5 bits in output. And this is the circuit of the diagram, but yeah, basically it's really like the cellular automaton with root 210 applied over 5 cells. Anyway, this is used as a nest box in the Ketchak algorithm that has been standardized as a cryptographic hash function. Now, the statement of the problem that we want to address with evolutionary algorithm is to see if you're able to find something that has good cryptographic properties. So the Ketchak S-box already has good cryptographic properties, but they are not optimal. So we want to find something that is either on par with Ketchak or better than that, and also with low implementation cost, because we said, okay, we want to implement this in hardware, for example, so we want to use something that is very compact. So we want to find a periodic boundary cellular automaton, where in particular we take the length of the cellular automaton, that is n, and moreover we will say that the diameter of the local rule will be equal to the state size. So dn is equal to d. What does it mean? It means that basically each cell, for example this one, will look at all cells here to compute its next state. And then the second cell will do the same, only that it will be like rotated in a circular fashion by 1 bit, and so on. So these are what are called in the crypto literature rotation symmetric S-boxes. They are cellular automata of a very specific kind, where you have the diameter that is equal to the same state size, basically. And okay, so we considered in our works, in our research, S-boxes from size 4 by 4 up to 8 by 8. And we use genetic programming to evolve what? To evolve the local rule of this cellular automata. So this is what it is nice about using cellular automata, because you don't need to evolve the whole S-box, you only need to evolve the local rule, basically. And the fitness function was targeting both nonlinearity and differential uniformity, so the highest possible nonlinearity and the lowest possible differential uniformity, and implementation properties as measured by the gate equivalent index, which basically tells you what is the, if I remember correctly, the equivalent number of NAND gates that you need to implement that particular circuit, that particular S-box. So you want that to be the smallest possible because of implementation's reason. for efficiency. So the results basically showed us that up to from n equal to 4 up to n equal to 7, we were able to find cellular automata rules that are inducing S boxes with optimal cryptographic properties, so optimal nonlinearity and optimal differential uniformity. And so this was even better than the Ketchuk S box in this way. For the case 8 by 8, actually the performances, for reasons that we are still investigating, the performances were quite worse with respect to the theoretical optimum. So we don't know if it is just a matter of the search space that is very huge and it explodes starting from 8 by 8 or some other reasons. And for the implementation properties, basically what we discovered is that the rules found by our genetic programming are able to be either on par with those of other encryption algorithms like Ketchuk, for example, the S-box based on the cellular automaton in Ketchuk, or also from other encryption algorithms like Present and Pico. So we have something that is either on par or slightly better, so they are slightly more efficient. And this is an example just to show you, like from a pictorial point of view, what is the structure of the S-box that is found by GP by evolving the local rule of this cellular automata. And okay, so we go to the last two topics that will be quite quick. Actually, I don't have a lot of slides here. Do you have any questions or remarks so far? Okay, so for this last part of the lecture, I will show you other representations to evolve Boolean functions, in particular Boolean functions rather than S boxes. And these other representations are based on combinatorial objects that are called orthogonal arrays. So let us recall a bit about resiliency and correlation immunity. So we said that basically a Boolean function is resilient or correlation immune of order T if the Walsh transform is equal to 0, so it's vanishing for all vectors that have an Hamming weight between 1 and T, okay? So this function here in particular is correlation immune of the second order, because you see here that all vectors of Hamming weight either 1 or 2, so 1, 0, 0, 0, 1, 0, 0, 0, 1 for those of weight 1, and 1, 1, 0, 1, 0, 1, and 0, 1, 1 for those of weight 2. All their Walsh coefficients are 0. So this is correlation immune of the second order. So except for the attacks like on the combiner model, correlation immune functions are also useful to what is called to construct masking countermeasures for side channel analysis. So we will have our guest lecturer on Thursday that will give his lecture on side channel analysis and how to perform this kind of attacks using deep learning. And the idea is that basically instead of attacking the mathematical structure of this encryption algorithm, you are attacking the concrete physical implementation of a cryptographic device. So once it is executing this encryption algorithm and encrypting some bits, there will be some physical leakages, like for example electromagnetic emanations, or let's say difference in timings between encrypting a 0 instead of encrypting a 1, or something related to differences in voltages and power, and you can exploit all this information to infer, if you have, like for example, an oscilloscope that is sensitive enough to get these differences, these signals, to infer what is the value of the secret key. So you are not attacking, let's say, the encryption algorithm from the mathematical point of view, but you are attacking it from a side channel point of view, so a side channel leakage. And in order to counteract this kind of side channel analysis, what you can do is a masking countermeasures, where basically you are employing a correlation immune function in order to make, let's say, the power values or the electromagnetic radiations the most random and uniform as possible. So the attacker has no means to infer the value of the secret key from the side channel analysis. So the idea is that correlation immune function can be defined beside using the truth table that we used here, also in terms of orthogonal arrays. And what are orthogonal arrays? So basically you have a binary matrix, let's say of n rows and k columns. And this matrix has the following properties. So if you take any submatrix of, so t columns at most, then you will see each tuple of bits appearing the same number of times. So you can see here in this matrix, for example, we are selecting the first, the third, and the fourth column. And if you look at the corresponding submatrix, you will see all triplets of bits occurring exactly once. Okay, so it is a permutation in this case. And this happens also if you select other subsets of three columns of the orthogonal array. So this is in particular with an index lambda equal to 1. So every triplet is occurring exactly 1. If you have a larger orthogonal array, you can have also indexes that are like 2 or 3. So it means that every triplet is appearing 2 or 3, exactly 2 or 3 times. And these kind of combinatorial objects have a lot of applications in statistics, for example, in the design of experiments, when you want to set up like your experiments, for example, for a treatment of a particular drug, and you want to have since you have like scarce resources to test this drug over a set of patients, you want to be sure that they are administered like this kind of treatment in the most balanced way as possible for statistical reason. Otherwise, they are used also in coding theory. Actually, these kind of orthogonal arrays are a breed of error-correcting codes that are called MDS codes, or also in cryptography. In particular, in cryptography, they are used here for side channel analysis for correlation immune Boolean functions. And we will see a bit on Thursday afternoon how they are also used in secret sharing. So how do we say that an orthogonal array can be used to characterize a correlation immune function? Well, basically, we consider, instead of the whole truth table of the function, we just consider its support. What does it mean? It means basically the set of input vectors that are mapping to 1 under the function f. So here you see this truth table where we have these 8 possible combination of input values. So if we just restrict our attention to the vectors that are mapping to 1, so the second, the third, fifth, and the 8th, then we have this smaller table here that is 001, 010, 100, and 111. This would be the support. And then you have this theorem that tells you that the function will be correlation immune of order t if and only if its support is an orthogonal array of strength t. So where t is the number of columns that you're selecting from the orthogonal array, and then you say, okay, this must appear the same number of times. So there is this correlation, there is this correspondence, let's say, between the strength of the orthogonal array and the correlation immunity order. Now, the idea is, okay, how do we use genetic algorithms or genetic programming to construct these orthogonal arrays? Because once we get an orthogonal array, then we know how to construct a correlation immune function. Well, the idea is to say, okay, each column of this, let's say of a candidate matrix, let's maybe draw it here. So we will have our binary matrix with k columns and n rows. And then we assume that this n is a power of 2. So it's 2 to the power of small n. What does it mean? It means that every column here can be interpreted as what as a truth table of a Boolean function, because it has size 2 to the power of n. So this would be a truth table. Okay, and then we can basically apply the same kind of genetic algorithms that we saw before for Boolean functions. Just we are applying them separately on each column of the orthogonal array. For GP, it's the same, but we have the additional step of translating the syntax tree with the truth table, the corresponding truth table of the Boolean function, and then interpret that as a particular column inside our matrix. So we start from this syntax tree, then we compute it for all possible combinations of the input. This will be a column that is a truth table of a Boolean function, and this will be, for example, the third column of our array that we want to be orthogonal. So in the same way, crossover and mutations, either in GA or GP, are always applied column-wise. So we just cross, for example, if we have two parents arrays. So we say, okay, we do the crossover between this column and this column, and then this column and this column. So first with first, second with second, etc. And in particular with genetic algorithm, you can still use the balanced crossovers that we saw before using counters, because orthogonal arrays have let's say, a monotone property, in the sense that if you have an orthogonal array of strength t, then it means that it is an orthogonal array for all k that are small than or equal to t. And this means in particular that if you take k equal to 1, so you're selecting a single column out from this matrix here, each bit at this point needs to appear the same number of times. So the same number of zeros, the same number of ones, which means that the column needs to be balanced, right? So you can still use balanced crossover operators. Otherwise with GP, okay, we said in the beginning that it is very difficult to find a crossover that is employing, it is preserving the balancedness constraint. So, okay, in that case, we are not, we just don't care about it, and we care for it at the level of the fitness function. So for crossover, okay, so basically this is, let's say, summarizing what I was telling you before now at the blackboard. So we use either counter-based crossover on each column for balanced genetic algorithm, or standard subtree crossover. For the fitness function, so we want to say, okay, we have a matrix like this, and we want to check how far it is from being an orthogonal array satisfying the condition of strength t. So what do we do? So basically, we consider each possible submatrix of t columns, and then we want to minimize the number of occurrences, so of tuples, that are deviating from the specified lambda. So you can see here from this example that we are, for example, considering the first three columns for this submatrix. And this submatrix, you can see here that we have 0, 0, 1, which is appearing twice, so 2 times. Then we have 1, 0, 0 that is appearing 3 times, 1, 1, 1 that is appearing once, and 0, 1, 1 that is again appearing twice. So here, for example, if we get lambda equal to 1, so we want each triplet to appear exactly 1, then we will say, okay, the deviation for each triplet will be computed by saying lambda, so the intended index, 1 in this case, minus the occurrences of that particular triplet. So 0, 0, 0 is not appearing, which means that we have 1 minus 0, which is 1. And then we sum everything for all the others, and in the end you get the deviation. And this deviation is just related to that particular submatrix. After that, you consider all possible submatrices, and you compute the fitness as the LP distance, in this case the Minkowski distance, between the vector that is optimal, so the vector where all occurrences are the specified index lambda, and the deviations, the vectors composed by the deviation of all submatrices. So this will be the fitness. And if it is 0, so we want to minimize this fitness, then we will get an orthogonal array of strength T and index lambda. And okay, this is the idea, and basically the results show again that genetic programming, again for some reason that we are not sure about why, is able to outperform genetic algorithms, even though genetic algorithms, again, are using a balanced representations and a balanced crossover and mutation operators. So now the very last topic for today is the fact of evolving constructions. What does it mean? So we said in this morning, if I remember correctly, that in the field of Boolean function, we have either algebraic constructions that are called primary, where you start from a set of particular combinatorial objects, like, for example, permutations, or what are called partial spreads that are particular families of vector subspaces. And then from there, you construct Boolean functions with specified properties, for example, being bent, so of maximal nonlinearity. Secondary construction instead worked by starting from a set of existing Boolean functions, and then you extend them to get new functions. So this is what they're called secondary. An example is the Rothaus construction, where you have like 3 Boolean functions, g, h, and k, such that g, h, and k are all bent, so of maximal nonlinearity, and also their sum, so their XOR is bent. And then if you define this new function that has like these 2 additional variables, x1 and x2, in this particular way, then you will get a bent function in n plus 2 variables. So the idea here is now, can we use genetic programming, or let's say some other kind of artificial intelligence optimization algorithm, to discover these kind of mathematical formulas? We use genetic programming to do this. Like in a paper that we presented last year in Gecko. So the idea here is that we have a set of seed functions, so predefined functions that are called here in the picture on the left. So we have, for example, f0 and f1, and we know that these f0 and f1, from their truth table, they already have optimal cryptographic properties, like having maximal nonlinearities and being balanced, for example. And then we will have also independent variables that are the variables that we need to add in order to get the secondary construction, so to extend our Boolean function. Then the genetic algorithm, the genetic programming is combining both predefined functions and independent variables as leaves in our genetic programming tree. And from there, we have, let's say, a Boolean function construction. So the idea is that we are not getting directly, like in the, let me write it here. So in the beginning, when we were doing direct search with genetic programming, we were saying, okay, we have the leaf nodes that are only input variables. Okay, so x1, x2, x3, x4, for example. Here instead we are saying we have leaf nodes where in some cases, depending on what genetic programming is doing with its stochastic genetic operators, we have the additional independent variables. So for example, we have V0 here. And here, for example, we combine it with one of the seed functions, so F0. And then we say, okay, you combine it by calculating the XOR of the output of this function computed on a predefined default input vector, plus the value of this particular variable. And then you can have something similar also here, like F1 and V1, and then here you compute the end, and then here at the end you compute the OR. So this is an algebraic expression that you get here at the end that is not giving you directly a Boolean function, but it is giving you a construction of Boolean functions, because depending on the type of functions that you put here in the leaves, then you get every time different Boolean functions. So this is the idea how you construct it with genetic programming. And actually what we noticed, well, first, okay, with genetic programming, we got something that was optimal in the sense that for the case of Boolean functions that we constructed with these kind of trees, starting from a particular set of seed functions, we were getting always maximum nonlinearity and balancedness, for example. And after that, we said, okay, first let's see if genetic programming is finding always the same solution, so always the same construction, only that it is, let's say, shrouded, hidden by the fact that genetic programming has this tendency to bloat and to do a lot of complicated expression. So first we use this particular tool for Boolean minimization, which is called Espresso. It's quite old, but apparently there is nothing, at least as far as I know, nothing newer than this. It was created in 1984, I think, or something like that. So basically you have a Boolean circuit, you give the description of Boolean circuit to this Espresso tool, and it will give you the minimal Boolean function or minimal circuit that is computing that function. And then after we minimize that, we also checked the equivalence between the best solutions, the best construction that we found. And actually many solutions turned out to be the same construction, basically, especially when only two seeds like F0 and F1 were used. And this is an example of a bloated GP construction that you can see here on the top of the slide. And if you simplify it a lot, then actually it turns out that it is equivalent to this very easy syntax tree. And the nice thing, well, very interesting, at least to me, is that many of the constructions that we found were equivalent to something that was already discovered by human mathematicians a long time ago. It is called the indirect sum construction and has this, let's say, this definition here. So you have the two additional variables v0 and v1 and the initial input vector v. And then you compute f of 0 over v if the first independent variable is 1. Or otherwise you do the XOR of f1 and v XOR v1, so the other independent variable, if the first independent variable is 0. So the first independent variable is working as a control variable in a certain sense. It's controlling what kind of output you get. And this is called the indirect sum construction, and it is quite interesting because see, okay, that even if genetic programming is like finding a lot of seemingly different solutions, in the end they, not always, but they turn out to be equivalent to this very well-known construction. So we dubbed this particular genetic programming as a lazy student because it seems like when you're considering, when you see like a student that is lazy and at the exam, like you ask, for example, to say, okay, solve this problem, but please don't use this solution because it is, let's say, very well known, so find something else, let's say, be creative. And then he or she starts to say, okay, I'm using the same, but then I'm mixing it with some random stuff just to add some entropy and look like if it is something completely different. So, well, jokes aside, actually, this is interesting because it could mean, for example, that what has already been found by human mathematician is, yeah, it's something that is already optimal. But we still don't know in the sense that we are ongoing with this experimentation. So maybe also something that is inequivalent to this construction will be found by genetic programming. In that case, that would be quite interesting because it would be that basically an artificial intelligence-based method like genetic programming can do, in a certain sense, mathematics.
Well, for now, mathematicians want AI 0.
Yeah, for the moment, yes.
Now.
I mean, for the moment, let's say that genetic programming was confirming, let's say, or it was like giving a support to say, okay, they already looked into some of the construction, human mathematicians, and it seems like there is nothing better, which is already some kind of contribution in a certain sense, in this, saying that, yeah, it has been found by human mathematicians and nothing more can be done, so we can look also at something else. But maybe we'll see in the future. So anyway, to conclude this lecture, so we saw how artificial intelligence optimization methods and also models like cellular automata can be used to solve some design problems in symmetric ciphers. So especially to find optimal Boolean functions and test boxes. The fact is that there are many more open directions to be explored. One of these is, for example, developing new algebraic constructions that we just saw. But also in general, well, we could take into account other primitives. So here we only targeted the so-called confusion layer of the substitution permutation network in a block cipher. So for example, so far as I know, no one tried to apply evolutionary algorithms to evolve permutation layers, so for doing the diffusion instead. And one could also, actually, this is something that is much needed, to be honest, would be to perform what is called the fitness landscape analysis for these search spaces. So you have your search space that is like something, I don't know, like a plane or something like that. And then for each possible candidate solution, you have the corresponding fitness value. And then you would have, let's say, some kind of surface over this plane that is defining the fitness landscape. And by doing some analysis of this fitness landscape, you can understand what is, for example, the structure of the local optima. And in this way, you can also get insight on how to, for example, initialize your evolutionary algorithm, or how to set its parameters in order to go to reach a good local optimum, or hopefully the global optimum, in a more efficient way. So this is something that in the future, personally, I will start like in my research line to investigate further. And then there are other open questions, but okay, I mean, I'm just pointing out these three because there are more than enough, I would say. And okay, so we are done for today. Do you have any question?
These open questions you meant as like in science or for our projects?
Can be both ways. Like it can be, let's say, these are in general not so easy to address in a single report like those that I'm asking you for the final exam of this course. But yeah, I mean, you can look into it and then just have, let's say, just also formalization of these open questions. That would be already something, let's say, doable probably for the exam, and then maybe something that in the future we can develop through collaborations into a full-fledged research or paper. So yeah, I'm not expecting that you're going to solve any of these in the span of a single PhD course. I mean, it would be nice if it happens, okay, but I'm not that. I don't expect this from you. Okay, so if we don't have any more questions, if the chat is okay on the. Okay, yeah. Then we can call it a day.